Hi everyone. In this video, we will be discussing the basics of flow circuit analogy. And basically, what we are trying to do is to relate what we have learned in pipe flow to electric current. So we'll basically go from pipe flow to electric current, and the idea is that we'll sort of relate these two in sort of an analogous way. And you have read a lot of things in electric current in freshman physics, and basically then you can carry over whatever you have learned in electric current back to pipe flow. And then there are some advantages of doing this, and we'll go over them like a little bit later. So before I go into electric current and the analogy with pipe flow, let me just briefly recap something about pipe flow because that's required to understand how we can relate it to electric current. So first thing is that this whole analysis is only for laminar flow in pipes. So please make sure that you do not get confused. This is only for laminar flow, which means that Reynolds number is less than 2100. So do not get confused and start thinking that this will be valid for any other cases. So this is only valid for Reynolds number less than 2100. Alright, so let us say we have a pipe and we know that when the length is L, diameter is D, and we are inputting flow rate Q, let's say, and the viscosity of the fluid is mu, density is rho. Then we have done this several times over that, and let me just also define P in and P out. We have defined several times that the two important dimensionless numbers in the system will be F, which is friction factor, and this will be a function of Reynolds number, where Re is Reynolds number, right? And to refresh your memory, friction factor is tau wall by rho u square by 2, where u is the velocity, or tau wall can also be written as P in minus P out into d by 4L. We derived that tau wall is equal to P in minus P out into d by 4L using force balance, and then this is by rho u square by 2 as before. Okay, so this is something we have already done, and then we call this friction factor as a ratio of shear stress to inertial stress. I'm just recapping few things that you already know, just in case you have forgotten them. And for Reynolds number, we know that that is rho u d by mu, right? And this is the ratio of inertial stress to viscous stress. Okay. So now, like I said, we are only concerned with laminar flow for flow circuit analogy, and you may remember that for laminar flow, we know that the correlation F is equal to 16 by Re, right? And that makes sense also because F is a friction factor is shear stress by inertial stress, and inverse of Re will become viscous stress by inertial stress. So inertial stress would basically cancel out in that sense, and that shear stress is only dominated by viscous stress, and that's true because Reynolds number less than 2100 means the flow is laminar or viscous stress dominate. Right? So we know this. Now I have written a definition of friction factor here, which is this one, right? And I have written a definition of Reynolds number, which I have now circled. So I'm just going to put back these things here. I will just say that this is P in minus P out into d by 4L into 1 by rho u square by 2 is equal to 16 by rho ud by, okay. And why am I doing this is that in through this way I can actually start to relate p in minus p out to velocity. And let me first just show you that we can cancel this out. This will become 2, mu will go into the numerator, so you can rearrange this. Mu will go to the numerator and there will be a d square here in the denominator, and then this u will get cancelled with square will get cancelled with this. So this basically becomes 32 mu u L by d square. You can cross check. This is what this becomes. Okay, so this is the relation which is sort of a standard relation for pipe flows in laminar regime. I will do one step further, something to sort again refresh your memory, that Q is nothing but U into pi d square by 4. That flow rate is pi d square by 4 in times velocity. I can replace U by Q by pi d square by 4. So I can write this as, in other terms, I can write this as P in minus P out will be Q times 128 mu L by pi d raised to power of 4. Okay. You can again cross check this and verify that this is correct. So what we are trying to now do is sort of we have gotten a relationship between pressure input, pressure in minus pressure out of pressure drop, absolute pressure drop, and flow rate. Now why we are doing this is that we can now start to bring in back the whole starting point of this video, which is closed circuit analogies. So initially here we had P in, P out, and then there is a flow rate Q going through the system. And now we have a relation where I am relating P in minus P out is Q times something I am calling as R, where R is 128 mu L by pi d raised to power of 4. Okay, and if I want to make this analogous to a electric circuit, what I want to say here is that let's say this is V in, this is V out, or voltage in, voltage out. The current is I and the resistance is R. We know that V in minus V out, or the potential difference or voltage, is equal to I times R. And here R is the resistance. What we are saying is that in pipe flow and electric current, there is the analogous thing is that P is similar to V, that voltage or potential rather, P pressure is like potential, so P in is similar to V in and P out is similar to V out. Q is similar to current, and the R of flow here, which I have written R here, R flow is an analogous to R electric, or the resistance due to electricity. So they are analogous to each other. And why is this even important? Why did I do the whole exercise of first finding out the resistance, flow resistance, and then sort of relating it to voltage? Is that now we can sort of see parallels between the two systems and start to use things that we have learned in electric current into pipe flow. For instance, in electric current, we know that if we have two resistors in series, then this is, let's say, V0, V1 here, and this is R1, this is R2. Then for two resistors to be in series, the current has to be equal because the same current has to flow through this system. And we say that the current is basically V0 minus V1 by R1 plus R2, and the effective resistance across the whole circuit is R1 plus R2 because this is in series, right? This is the series system. Now if I want to draw parallel to the flow circuit analogy, is here I will have two pipes in series. Let's say this pipe, and then there is another pipe here, and this has length L1, this has length L2, this is diameter D2, and this is diameter D1, and then there is flow rate Q, rho and mu. Fluid is the same, and this is P in here and this is P out here. And if I want to find the flow rate, what I can do here is that I can write Q is P in minus P out by R1 plus R2, where R1 is, we can go back and use this formula we have, which is 128 mu L by pi d raised to power 4. So we can write R1 as 128 mu L1 by pi d1 raised to power 4 plus and R2 as 128 mu L2 by pi d2 raised to power 4. So this way we have combined the what our understanding from electricity into pipe flow without really solving anything. So we didn't have to solve anything. We could just add up the two resistances of this pipe and this pipe and write the whole equation. Now note, this is series because the flow rate has to be same. So whatever flow is going in this pipe, in the first pipe, has to be in this pipe, has to be going through this pipe, because the mass has to be conserved. We cannot have any flow which can accumulate in the first pipe. It has to go into the second pipe. So the flow rate in the two pipes have to be the same. Similarly, because the current has to be the same in series. So we added up the resistances. There could also be a case of parallel system where we have same potential across the two systems. So where we have same potential. So this is I, this is I1, I2, this is V1, V0, and this is V1 here. This is R1, this is R2, right? And we basically say that in parallel circuits, the 1 by R effective is 1 by R1 plus 1 by R2, or R effective is R1 R2 by R1 plus R2, right? So the total current I is V0 minus V1 by R effective. This is something we know from circuit electric current. So now if we want to have something in pipe flows, we'll have, let's say, pipe here and a bigger pipe here, and some water will be flowing from the same pressure line, that the P in is same here and P out is same at the exit. At both the exits the pressure is same and like similar in inlet, and this is D1, this is D2. Let's just say the length is same for both these pipes. Then if we have to find the total flow rate, not just Q1 or Q2, we have to find total flow rate. We'll say that Q1 plus Q2, or total flow rate Q, is P in minus P out by R effective, where 1 by R effective is 1 by R1 plus 1 by R2, and we know R1 is 128 mu L by pi d1 raised to power 4, and R2 is 128 mu L by pi d2 raised to power 4. Okay, so we have again carried over the understanding from circuits that the total current is V0 minus V1 by R effective. Here total flow rate is similar to P1 minus P out by R effective. So it's basically sort of simplifying life. You can have two pipes in series, and then third pipe is in parallel. Then you have solved these kind of circuits in electric current, and then you can basically get the effective resistance of the system out, and then find the flow rate, or if the flow rate is given, you can find pressure drop and things like that. So just briefly review the whole video once so that you can remember everything. So we started by talking about flow circuit analogy, and that there is some similarities between pipe flow and electric current. Basically, pressure is similar as potential, flow rate is similar as current, and the resistance is derived, and the flow resistance is similar to resistance in electricity. And this whole analysis is only valid for laminar flow, where Reynolds number is less than 2100. So we said that for a pipe of length L, diameter d, viscosity for a fluid with flow rate Q mu rho, we know that friction factor is a function of Reynolds number, and then from there we know for laminar flow friction factor is basically 16 by Re. By using the definitions of friction factor and Reynolds number, we found out a expression for P in minus P out versus physical properties and velocity, which then, because we wanted to convert into flow rate, which is similar to current, we converted the expression into flow rate. Now from here we started making similarities between pipe flow and electric current, and specifically we said that pressure is similar to potential, flow rate is similar to current, and then the resistance, we found the expression of resistance for flow resistance. Now in series, the flow rate is same in pipe flow, and current is same in electric current because they are analogous. So the resistances are added, the total resistance becomes R1 plus R2, and similarly in current, and similarly in pipe flow, and then we can just write down the values of R1 and R2. So lastly, we discussed parallel case, where the pressure difference is the same and the flow rates are different, but the total flow rate can be found by using P in minus P out by R effective. Similarly in current, where you have the voltage difference to be the same, and then you can find out R effective by using 1 by R effective is 1 by R1 plus 1 by R2. Again, we have already defined the value of R1 and R2 using the formula that we had discussed, which is 128 mul by pi d raised to power 4. So I hope like you could sort of see the usefulness between flow, pipe flow and circuit, and analogous relations between pipe flow and circuit, electric circuit, and now we will basically be doing one problem. In the next video we will be actually using what we have learned here to solve the problem. So I hope this video was useful, and as always we'll be happy to take any feedback.